Hello everyone, my name is Harshali and I'm going to explain about bit manipulation today. So first let's start with binary number system. So in binary number system we represent numbers in powers of 2. So let's consider these boxes as a digit and let's take this as 2 power 0 and 2 power 1, power 2, 2 power 3 and 2 power 4. And all these will result to this will be 1 and 2 power 1 is 2, this will be 4, 8 and 16. Now if you want to represent the number like n equals to 10, so how we'll represent this is uh, so as we know this is 1, this is 2, this is 4 and this is 8. So 1 and 1 because 8 plus 2 is 10 and all these will be 0. So the binary representation of 10 will be 1010. And we keep it in brackets and write 2 here to know that this is a binary number. Now, let's take another example. Suppose we want to represent something like 14. So how will we represent this? Again, this is 8, this is 4, this is 2 and 1. 14 will be something like 8 plus 4, which will be 12 and 13, 14, which is 2. So it will be, and this will be 0. So this will be 1, 1, 1, 0 and base 2. So this is how we represent binary numbers. Now let's see the data types. So there are four types of primitive data types. Okay, which are integer, float, character, and the last one is boolean. So let's start with integer here. So integer is generally of 4 bytes. So 1 byte is equal to 8, it's equal to 8 bits. So if we want to know how many bits are there in 4 bytes, we can just multiply 4 into 8, which will be 32 bits. It means that there are 32 boxes. When you think of a number which is of integer, it's represented in a block which has 32 bits. Now, let's see what is the range of integer. So, when I say range, I mean the highest, the minimum number which you can represent and the maximum number you can represent. So, in this range also, there are two types. One is unsigned and another one is signed. So first, let's talk about unsigned. So in unsigned range of integer, it means let's say we have 32 boxes. I'll be representing MSB, which is the most significant bit, and this will be the last one, which is LSB, least significant bit. Now this is the 1 and 32. So in total, there are 32 boxes because, like we saw just now, it has 32 bits. Now, unsigned means that there are no negative numbers. It means the number does not have a sign. When the number does not have a sign, like 2, 5, 10, we consider it as positive. So it's not negative. And when we say signed, it has a sign like -5. So it's a signed bit. So we won't be discussing about this. We will be seeing unsigned first. So it has a range of 0 to 2 power 32 minus 1. Now let's see why does it have a range. Okay, let me write it a little down. Okay, so let's see it. Its range will be 0 to 2 power 32 minus 1. Now why we say it has 0 to 2 power 32 minus 1 is because the lowest number which we can represent will be all 0. So this will result in 0. Okay, so when I say the range is 0 to 2 power 32 minus 1, the minimum you can represent is 0 and the maximum which you can represent is 2 power 32 minus 1. Now, why is it 2 power 32 minus 1? We will understand with an example taking a number of 2 bits. Okay, so when you take a number of 2 bits, let's think of the possible combinations we can represent with these two. So one would be 0, 0, another one would be 0, 1, then 1, 0, and 1, 1. So the number of numbers we can represent will be 2 power 2, which is 4. So there are 4 numbers, but the maximum number is 1 and 1, which is nothing but 1 and 2. So 2 plus 1 is nothing but 3. So this is the maximum number these two digits can represent. In the same way, the maximum number 32 bits can represent will be 2 power 32 minus 1. Okay. Now, once we are done with the unsigned bits, let's go to signed bit. In signed bit, we can represent negative numbers also. So -5 or -32 or something like that. So when you see there is a sign, that is why you know that you can represent negative numbers also. So in this, the range will be -2 power 31 to 2 power 31 minus 1. Now let's understand why. And let's understand how you represent a number is negative or positive in this case. So let's again take a number of 32 bits. This is the most significant bit and this is the least significant bit. So when you write 0 in the most significant bit, it means the number is positive. But when you write 1 in the most significant bit, it means the number is negative. So so now let's take an example. If you want to represent something positive, you'll write 0 here. And if you want to represent something negative, you write 1 here. Now, why is the range 31 and here 31 minus 1? So this happens because there are two ways to represent 0. Now, when you represent 0, let's take these again are 32 bits. When you want to represent 0, one way is to represent this way, which means a positive 0. And another way is this 1 and 0, which means a negative 0, which doesn't make sense, right? Because there is nothing as negative 0. So what we do is we don't consider a negative 0. So we consider a range which has 2 power 31. 31 because we won't be considering this as this is the signed bit. So only 31 bits are left in which we can do. And 1 is 0, so -1. And the other side would be 2 power 31 because there is no negative 0 here. So that is why the range of this is 2 power minus 2 power 31 2 power 31 minus 1. Okay. So next is float. This is 4 bytes, and float means you can represent numbers with a decimal point like 4.32 or 5.16 or pi 3.14. And this can go up to 7 decimal digits. And then the double, if you want more than 7 decimal digits, then you can use double, which has a size of 8 bytes. So you can represent up to 15 decimal digits here. Okay. And the other two ones are characters, which can be represented with 1 byte. So character is basically something like maybe you want to represent a percentage, or you want to represent a letter, or maybe some special character, something like that. Another one is Boolean, which also has a size of 1 byte. And in this, you can represent a 1 or a 0. So 1 is basically true and 0 is false. Then let's see what are type modifiers. Right. So type modifiers. In this, there it is unsigned, signed, short, and long. So when you add this in front of, let's say, you say short int, it means the value of the size of this will become 2 bytes. It means when you don't want to, this is used when you don't want 4 bytes of data and you're sufficient with only 2 bytes. And another case is long int, where you want more than 4 bytes of data. So you do 8 bytes. This will become 8 bytes when you add long to the int. And unsigned and signed, if you write unsigned int, its range will become, you will have more range. You use the unsigned integer when you know for sure that you won't be needing a negative value. For example, if you want to calculate time, okay. So there is no negative in time. So you can use a unsigned integer for that. This will also give you a better range. Okay, and next let's see about types of operations, types of bitwise operations. Okay, types of types of bitwise operations. So let's start. I'll mention all of them. One is AND operator, another one is OR operator. This is XOR operator, then right shift, and then left shift. So now let's understand each of them in detail. So, AND operator, when you do AND between two bitwise numbers. Okay, so let's consider A and B. So, the result of this uh, is determined by a table. So, there is AND table where we take A and B and we take all possible combinations of it and we do A and B. So, 0, let's take 0, 0, 0, 1, 1, 0, and 1 and 1. So when these two when these two are 0, so nothing is 1, so it's 0. 0 and 1, no, it's still 0, this is also 0, and 1 and 1 will only be 1. So this is the table for and based on what A and B are, we can determine what is the answer of this. Now let's consider that we have two numbers, say 1, 0, 1, 1, and another number 1, 1, 1, 0. And you want to do AND operation between these two. So what we'll do is 1, 0, 1, 1, 1, 1, 1, and 0. So the AND operation between 1 and 0 is what? 1 and 0 is 0. So this will stay 0. 1 and 1 is 1. So this becomes 1. And 0 and 1. 0 and 1 is 0. So this stays 0. And 1 and 1, again 1. So the AND operation between these two will be 1, 0, 1, 0. So now next let's see OR operation. Or this is just a line. OR operation. Again the same thing, A or B. So in this what the table will be, let's see. OR table. This is A and B, A or B. So this is 0, 0, 0, 1, 1, 0, 1 and 1. So 0, 0 will be again 0, 1, 0 or 1 is 1, 1 or 0 is 1 and 1 is once again 1. Now let's see an example of this. 1, 0, 1, 1 and 0, 0, 0, 1. So 0, 1, 1, 0, 0, 0, 1. We want an OR operation between this. So 1 and 1 is, let's see, 1. 1 and 0 is 1. 0 and 0 was 0. And 1 and 0 was 1. So the OR operation between these two will be 1, 0, 1, 1. Now let's see XOR operation. So XOR operation is represented by this, just Z, X, O, R. So to remember this operation, you can remember it as a switch. So let's take A and B again, and A XOR B. So again, condition 0, 0, 0, 1, 1, 0, 1, and 1. So what we will be doing in this is, it's like a two-way switch, where if both the switches are off, it is off. But if one switch is on, then it's on. If one switch is on, again it's on. But if both are on, it's off. So 1, 0, 1, 1, 0. And an example for this, let's write it here itself. Okay, so 1, 1, 0, 0, and 0, 0, 1, and 1. Let's do XOR operation between them. So let's take another one also. It is 1 and 1. So this becomes 0. This becomes 1, 1, 1, and 1. So the XOR operation between these two is this. And then next, let's see right shift. This is right shift. We can see the direction it's facing rightward. So this is right shift. Now in right shift operation, what happens is it moves the number a bit towards right. So one bit is shifted to the right. Let's take an example. Let's take n equals to 10 and we will shift this to right by 1. Okay, so how is 10 represented? Let's say 8, 4, 2 and 1. So 10 is 8 and 2, 0, 0. So 10 is nothing but 1, 0, 1, 0. Now, what a right shift means is 0, 1. So this is what 10 is. Now, when you shift it to the right, it means that this digit is discarded. This goes in zero's place, and this goes again here, and this 1 comes here, and all these are of course zeros, and this digit is discarded. So this becomes 4 and 1, right? So this becomes 5. So when you do right shift, it decreases. Let's take another example and understand this. So n equals to 14 or maybe 13, let's say. So 8, 9, 10, 11, 12 and 13. So 13 is represented like this in binary form. Now let's see what happens when you do right shift to this. So this is 1, 0, 1 and 1. Now when you do right shift to this, let's see what happens. So 1 is discarded and then 0 comes here, 1 comes here and another 1 comes here. So what this becomes is 1, 2, 4, right? So 6. This becomes 6. So this is what happens in right shift operation. Now let's see left shift. In left shift operation, uh, let's take n equals to 15. So 8, 4, 2 and 1. So it will become 1, 1, 1 and 1. So 8, 9, 10, 11, 12, 13, 14 and 15. So in left shift operation, this is 1, 2, 4, 8. So 1, 1, 1 and 1. But when we do a left shift operation, we will add a 0 over here and shift all the other elements towards one bit to the left. This is 1, again 1 and 1. And these are of course 0 before all this. So let's see what happens to this. So this is 1, 2, 4, 8 and 16. So this becomes 16 plus 8 plus 4 plus 2, which will be 16, 17, 18, 22 plus 8, which is 30. Right, so this number increases. Now let's take another number which is n equals to 2. Let's take a small number. So 2 is represented as 1 and 0. Now if you do left shift to this, it becomes 1, 0. Because one shift here, and an additional 0 is added. So this becomes 1, 2, 4. So this becomes a 4. Okay, so the first problem we will be seeing in this will be to check if ith bit is set or not. Now in this, what is the meaning of set? So when a bit is 1, it means the 0th and first. So first bit is set here. Okay, so if it's 0, then this is not set. So set basically means 1. So now we have to check if ith bit is set or not. Now, in the question, they will give you what is I and what is n, and we have to find out if that position of the number n is 1 or not. So, I'll explain the question. Let's take n is 1, 0, 1, and 1, 0 again. So, if they ask you 0, 1, 2, 3, 4, let's index it this way. And if I is equal to 3, so I3 in number n is 0, so it is not set. So this is what they are asking. Now let's see how can we solve it. So before solving this, let me tell you, you remember we did and or operations, right? So when we multiply any any number with 1, it returns 1 only when both of them are 1. Or if it's any other case, it returns 0. So we can use this to our benefit and we can multiply the bit with 1. And if the result is 1, it means, sorry, I meant AND operation, not multiplication. So when we do AND operation with 1, and if we get 1, it means the bit is set. And if we get 0, it means it is not set. So what we will do? is we can't multiply it in the middle of nowhere, right? So we will drag this to the right to the least significant bit. So how can we do this? Is we will just do right shift. This is the right shift operator. Okay. So now how many to the right? So in this case, what we have to do is bring this to this. So one, two, three positions to the right. It matches the I. So what we need to do is we need to bring it three positions to the right. So it will be N right shift I because I is 3 and N is the number. So how will we write it in code? Let's see that. What if ith bit is set or not? Now let's take N equals to any random number 18 and I equals to 3. And now what we will do is if what we are doing first N right shift I and right shift I, and if that digit multiplied by 1 is equals to 1. And now if this is equal to 1, which means that the ith bit is set, or else it is not set. Now let's run this and see. Now what will be the answer of this? 18 and 3, right? Let's see it again. So 18 is N and 3 is I. So this is 1, 2, 4, 8 and 16. So 18 will be 1, 16, 17, 18. So 1. So this 2 will be 0. So 1, 0, 0, 1 and 0. And I equals to 3. So 0, 1, 2, 3. So the answer which we will get will be not set because this is not 1. So let's run this and see. We need to get not set. Okay, let's remove this one as well. And now let's see it again. So this is not set. Now let's check which one was set. So this one was set. This is what? This is 3. So this will be 4. Now let's check with 4. 4. Now let's run this and see again. It should be set. So this is set. So this is how we check if ith bit is set or not. Okay, now let's go to the next problem, which is the second one. This is counting number of set bits. So if a number is 10010, if a number is this, let's count how many number of set bits are there. So manually 1 and 2. So the number of set bits are 2. Now, how do we program this? So what we will do is we will keep this in a loop. So when we put it in a loop and we'll keep multiplying every number with 1. And whenever we multiply it with 1 and the output is 1, we will add to our counter. Keep a counter variable and we will add plus 1 whenever we get an output of 1 from the multiplication. So basically what we will be doing is we will be going in a loop like this. Okay. So basically we will be shifting this number to the right and we will count and the least significant bit will be analyzed every time we go. So let's see 0. 0 is multiplied, sorry, and with 1 we get 0. So nothing happens. And then we will cancel it out. We will right shift the number. So now our least significant bit will be this. Then we do AND operation with 1 and then we get 1. So whenever we get 1, we will increase the count operation. So this is how we do it. Now let's see it in practice. Coming to the main part, what we will do if n and 1 is equal to 1, we will increase the counter by 1. So count plus plus is nothing but count equals to count plus 1. Now let's check. We are getting 2. Here the number is 3. So when n equals to 3, it's represented as 1 and 1. So it has two ones. So we are getting correct answer. Now let's check for n equals to 18. And this also should give us 2. 18. Let's run this. Okay, there is no difference. Let's check another number which has more ones. Okay. So 1, 1 and 1 and 1. So 1, 2, 4 and 8. 8, 12, 16. Okay. Sorry, 15. This will be 15. So 4 ones, right? See, we got 4. So that is how we check the number of set bits in a binary number.